Hello, Year 12. This is me pre-recording the lesson going through these questions. So we both get a little bit of time on a Friday to ourselves. You can watch this video and I can get on with some work for next week. So some of you can fast forward to the questions that you got stuck on, or you can watch me just work my way through these. Right, define the term standard enthalpy of formation. The enthalpy change when 1 mole of a substance is formed, from its elements in their standard states. I think I'll put everything in the standard state. Keep it 1 mole of a substance is formed from the elements in the standard states. 3 marks. Alright, for learning a definition. Alright, that's steady away, isn't it? That really is just something that you've got to learn. Use the data in the table to calculate the standard enthalpy of formation of liquid methyl benzene. In the background here, I'm just scrolling through the mark scheme just to see why that's 3 marks. It seems so easy to get 3 marks. Enthalpy change when 1 mole of a compound, 1 mole of a substance, I said. Yeah, 1 mole is formed from its elements with everything in their standard states. All in the standard states. Okay. So, use data in the table to calculate the standard enthalpy of formation of liquid methyl benzene. Whoa, wobbly stand there. Liquid methyl benzene. There's the equation. Oh, they give you the equation. That's nice of them. What have I got? I've got the combustion of carbon. So I've got 7 times that. I've got the combustion of this. And I've got the combustion of this. Right, the combustion to burn this would be minus 3903. To burn this is going to be 4 times minus 286. To burn this is 7 times minus 394. Down at the bottom it doesn't ask for it, but you would make 7 carbon dioxides and 4 H2Os. Okay, doesn't ask for that, but you'll know. Right, so the alternative route, so if I wanted to work out x, the alternative route is this. X equals 7 times minus 394 plus, because I'm going with this arrow, 4 times minus 286. We're going against this arrow, so that's minus 3909. Put it together, what have you got? Bibbidi wobbidi boo. Right. What's that film? Answers in the comments. Minus 394 plus 4 times minus 286 close brackets minus. I know that's a plus. Plus 3909. 7? Interesting. Yeah, 7 plus 7 kilojoules per mole. Brill. That's quite a low value, isn't it? Normally they're bigger than that, but an experiment was carried out to determine a value for enthalpy of combustion. Ooh, just look at all that heat loss going out through there, and all that heat loss through there, and all that heat loss through there. Anyway, container with some water, they're going to burn some methyl benzene using the apparatus shown in the look. They're burning 2.5 grams of methyl benzene, so that'll give me a moles. Cause the temperature of 250 grams of water, so that's my M, to rise by 60 degrees C, that's my delta T. Use this information to calculate a value for the enthalpy of combustion of methyl benzene. Alright, so we do 2 parts. Q equals MC delta T first, that gives us a value in joules. And we also work out the moles, then we can put them together. M equals 250. C equals 4.18. Delta T equals 60 degrees. So we do 250 times 4.18 times 60. Haven't laid this out particularly well. 250 times 4.18 equals times 60 equals, that's how many joules? 62,700. 62,700 joules, which is 62.7 kilojoules. Moles, I've got 2.5 grams, so if I divide it by the MR of methyl benzene I think was up here somewhere. C7H8. So C7H8, 7 times 12 the MR I'm doing now. 7 times 12 equals plus 8 equals 92. MR equals 92. 2.5 divided by 92. This tells me the number of moles that I've burned. 2.5 divided by 92. So I've burned 2717 moles. That's worth a mark in it. Mark there, maybe a mark there, maybe a mark there, I don't know. Final thing then is 62.7 divided by 0.02717. And that'll give you kilojoules per mole. I've run out of space. You get much more space in the exam for this. 62.7 divided by 0.02717. 2307.7. 2307.7. Sig figs. Well, I'll do that, and then sig figs is going to be 2 sig figs, but it doesn't actually say that in the exam. They're not bothered about sig figs, but it would be 2,300 if we were doing sig figs, kilojoules per mole. There's your answer, anyway. A 25 centimetre cube sample of hydrochloric acid was mixed with most solutions were initially 18. That's the thing I was talking about today. If they have to be both the same temperatures, if you're going to mix them, you don't want to put like ice cold into something, or you don't want to pour loads of hot water in and then try and measure the temperature change. Okay, use this information to calculate a value. Right, what have we got? 25 of 2 molar. 25 of 2 molar. You've got 50 of 1 molar. 50 of 1 molar. I can already see the moles of each are going to be the same. Temperature of the final solution. They were initially 18 and the final solution was 26.5. So delta T equals 8.5. Mass 75. So Q equals MC delta T part, and then there's a moles part. Mass is 75 times 4.18 times 8.5. Moles equals 50 times 1 divided by 1,000, or 25 times 2 divided by 1,000, the same deal. 50 times 1 divided by 1,000. .05 moles. Joules, 75 times 4.18 equals times 8.5 equals 266 joules, which is 2.664 kilojoules. Final thing, there's your moles, there's your kilojoules. Divide one by the other. 2.664 divided by 0.05 equals 53.28 kilojoules per mole. I'm doing alright, yeah. Cool. I've not practiced them. Okay? Never do. Don't mind making mistakes in front of you. I just want you to see how somebody with a, who's quite good at chemistry goes through these things. But I want you to show you that it's not, practice what you preach and all that, innit? It's important. Give one reason why your answer to part D has a much smaller experimental value than your answer to part C. What? Experimental error. Yeah, okay. Well, this one is losing heat from here, here, here before it even gets to the water. That's losing heat all over the place. This is going to have less heat loss because it's just done in a beaker. It's just less heat loss. The burning ones, the combustion ones, have just got heat loss all over the place. If you light a match, the heat just doesn't just go up into the water. It goes in all directions. So that's the idea there. I'm pretty sure. I don't know. Yeah, less heat lost. Question 5. Write an equation for the complete combustion of propanone. C3H6O plus oxygen, leave a gap, makes carbon dioxide and what? God, even telling you what it makes. 3 carbons, 3 carbon dioxide, 6 hydrogens, 3 waters, 6, 7, 8, 9 oxygens. There is an oxygen here, so you need 4 O2s. In a laboratory, you know, that catches people out, but I've practiced them so often that I just look out for it. In a laboratory experiment, 1.4 grams of propanone, so there's a moles for you. Okay, 1.4 grams of this stuff, C3H6O, was burned completely in oxygen. The heat from the combustion was used to raise the temperature of 100 grams. There's your mass from here to here, so that's going to be your delta T. Right, delta T, 351.2 minus 293.1. Delta T is 58.1. Right, calculate the number of moles of it takes it down step by step. Alright, 1.45. So you're doing the moles calculation first, divided by the MR of that, 12, 24, 36, 42, 52, 58. 1.45 divided by 58. Moles, 1 over 40, 0.025. This looks like a very easy question to me. That's famous last words, isn't it? Calculate the heat energy required. Heat energy is Q, so Q equals MC delta T. M is 100, C equals... They don't come this easy anymore, I don't think. 100 times 4.18 times 58.1. 100 times 4.18 times 58.1. 24,24285.8 joules. Does it ask for it in kilojoules? Doesn't even ask for it in kilojoules. Does it ask for it in sig figs? No. But 4 sig figs, maybe I'll do 4 sig figs. 2, 4, 2, 9. Was it 3 sig figs? Oh yeah, 3 sig figs. 2, 4, 3, 0, 0, 0. But anyway, it doesn't, so there you go. Hence, calculate value in kilojoules per mole. So that's 24285. So that's 24.2858 kilojoules divided by 0.025 moles. I'm going to divide that by 1,000. 0.025, I'm getting bored. I'm not bored like because I don't like chemistry, just bored because I'm tired and I want to finish working today, but it's just saving me time tomorrow. Focus, Norton, focus. So that's 971.4, 971.4, and there's that thing, and I am going to call it the Mansell effect, where she brought it up in the lesson. You've got to now decide what sign to put on that, and it's exothermic because it got hotter. Minus 971.4. I bet it gives you a range in the answers. It looks through. Yeah, you're allowed a range because you some people might round differently. Right, in a similar experiment, the enthalpy of combustion of C4H8O was found to be this many kilojoules per mole. A data book value has the same reaction. So they did an experiment and they got this. But the data book said it should have been this. Suggests one reason why the experimental value is very different from the data. Because the experiment is rubbish because of all of the heat loss. Alright? Heat loss, heat loss, heat loss. Alright? That is why there is a significant difference. It says on the marketing, don't allow incomplete combustion. I think it's because it's like, why is it such a massive difference? And the massive difference in combustion reactions is always heat loss to the surroundings. The difference... So it suggests one reason. Okay, the data book value is minus 2430. It refers to the formation of carbon dioxide gas and water in the gaseous state. How would the value differ if it referred to the formation of water in the liquid state? Well, the difference. You've got gaseous water. If you formed liquid water instead, So it's exothermic. My hunch tells me that if you formed liquid water, what happens when you form liquid water? When you form liquid water, water molecules form attractions to each other, so give out heat. My hunch tells me that if you formed liquid water, it would be more exothermic. I mean, you don't form liquid water. It's a bit of a strange question. If you form liquid water, when gaseous water turns into liquid water, you form more attractions, and when you form attractions, it releases energy. That's what I'm going for. That is an odd question. What's the answer? It's more negative. Is that what I said? More exothermic. Yeah, more negative, more exothermic, because heat is released when water vapor condenses. Because I thought it'd be like, because it's an it's strange this, I've not seen this question before. I just thought, because if you're going from gaseous water to liquid water, so it's an exothermic reaction, and yeah, making bonds between water molecules, or making hydrogen bonds between water molecules, releases energy. Tough. You know what, you'll come across them in the exam and they'll make you think, and you won't know for sure whether you've got them right. But what you lot will know for sure is you're getting all the calculations right. So that's fine. Think of it as a differentiating question. You know, anyway, give it a go. Calculate a value for the standard enthalpy of formation for liquid ethane thiol. These are old questions because they're giving you the equations. Very similar to that one we had before. Okay, you got the combustion of this, so you're going to burn that minus 170. So arrow's going down, you're burning it, turning it into something else. Carbon, that's 2 times minus 394. Hydrogen, 3 times minus 286. And you're going to burn sulfur, minus 297. Your alternative route to work out this is going to be against those 4 arrows, and no, with those 4 arrows and against that one. So x equals 2 times minus 394 plus 3 times minus 286 plus minus 297 minus 1170 minus 1170. You know what? It's late. I can't be bothered plugging all that in. That's quite a straightforward one. Yeah. Quite easy, that, isn't it? Anyway, a student carried out an experiment to find the temperature rise for a reaction between hydrochloric acid. Look at this. I like this question. They used a measuring cylinder, 50 of one stuff in hydrochloric acid. They recorded the temperature at 1 minute intervals for 3 minutes, exactly as I described the other day. At the 4th minute, the students added the other chemical, exactly the same number of moles, and stirred to mix the solutions, but they did not record the temperature. Look, they did not record the temperature at the 4th minute. The student recorded the temperature at 1 minute intervals for a further 8 minutes. I'm going to pause the video, plot this graph. I'll be back to you in a sec. It'll magically appear. Terrible printing of the graph paper, but we'll give it a go. Actually, I'll just come back in here. I haven't drawn the graph. It hasn't magically appeared. I just froze the video then. Take your time to work out the axis. Alright, this is the hardest bit of this. There's 12 marks across, 12 across, that's going to be straightforward. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I just took a minute or so to realise that you can't quite do 0.1 for each square. So I'll get back to you when I've got my own axis coming up. 1 sec. Oh, you can, but yeah, it doesn't. Blah blah. You'll see in a minute. Right, there's my axis taking shape. Sorry, I meant you do 0.1 per square. I wouldn't. You'll get penalised if you make it too small. So my range of numbers goes from 19.8. So I didn't want to put 19.8 on this line. You don't have to start at 0. There's no point starting at 0. What a waste of a graph. The important stuff is happening between 19.8 and 20. I didn't want my point to be touching this bottom line, which is time, and this is temperature in degrees C. So I started 19.8 there, 19.8 across here, and then I tried it 2 squares per 0.1, didn't work, and then I went to 1 square per 0.1, and that works because my data goes up to 21.1, but I've gone a bit higher because it'll go higher when I extrapolate the graph, I imagine. If you take your numbers right to the very top, when you extrapolate the graph, I bet you end up going off the graph. Anyway, pause. I'm stupid. Just made a mistake. I read it wrong. Goes up to 21.7. I'm going to use the whole space. Back in a sec. Okay, here's a continuation of me making a total hash of this question then. I didn't want to print it off again, so I'm just going to make do. And so learning point for me there, think harder about scales. 5 minutes is 21.4. 6 minutes is 21.7, so it's still warming up. 7 minutes is 21.6, so it's cooling down. Am I going to end up off the graph? I might well do. 21.5, 21.4, 10 minutes, 21.3, 11 minutes, 21.2, 12 minutes, 21.1. I've made a right muck of this. A right muck of it. Oh, have I got away with it? Me lad's little Star Wars ruler. I think I've got away with it just. If I extrapolate that back to the 4th minute, it just fits on. Oof, what a shambles. I think I've used every possible inch of this, and I don't think I should have. Anyway, you can laugh at me for being incompetent. Delta T is from 19.7 all the way to 21.9. 21.9 minus 19.7. 2.2 degrees C. Right, what did I get then? What have they asked me to do? Results shown in the table. Use your graph to work out delta T at the 4th minute. 2.1 it says. I said 2.2. 21.9 minus 19.8. Because I plotted it in 19.7. You doofus. I'm making a total mess of this. 19.7. Don't do work this late at night. Alright, don't do work this late at night. Of course it all fits on the graph. It starts at 19.8. 2.1. I drew my points at 19.7 because I didn't bother reading the table. I thought I'd remembered it. I hadn't remembered it. I'm a disgrace to chemistry and to teaching. But I refuse to do the work again to make it better. Alright, 2.1. The uncertainty in each of the temperature readings from the thermometer used is plus or minus 0.1. Calculate the percentage uncertainty in the value for the temperature rise. So that means that a temperature rise has got 2 temperatures. It's got a temperature at the top and a temperature at the bottom. So the total uncertainty will be 0.2 divided by the temperature rise, which will be 2.1. 0.2, let's have a check of that. Bet I'm right there. Oh, he's back on form. 9.5%. Suggest a change in the experiment that would minimise heat loss. Right. Minimise heat loss. Well, that's quite easy, isn't it? Put it in a polystyrene cup. Put a lid on it. Wrap it in cotton wool. That'll do, innit? Don't do it in a beaker. I bet she does it in a beaker, doesn't she? She? I think this is the one with a she. I'm really sorry if I've just been inherently just chosen that it was a girl doing it. A student. There is one with a girl doing it, sorry. A student carried out the experiment. A student. He. Let's say he. He didn't do it right. He put it in a glass beaker. Wally. Wally. Suggest and explain another change to the experiment that would decrease the percentage uncertainty, but you're using the same thermometer. So percentage uncertainty, if you're using the same thermometer, that is going to be constant 0.2, but you can decrease the percentage uncertainty if you can make this number bigger. How could you make that number bigger? So you need a bigger temperature change. So use more concentrated solutions. That will give you a bigger temperature change. Yeah, did that work? Let's see what it says. Yes. Yes, 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 yes. A second student completed an experiment to determine the enthalpy of neutralization for the reaction between ethane dioic acid solution. It looks like this, ethane dioic acid. It's got a carboxylic acid on each end. And potassium hydroxide solution. The students added this much ethane dioic. Right, so what's going to happen here? The equation is this. I bet you struggled on this one. When you add potassium hydroxide to this end is an acid and this end is an acid. You're going to make this salt. I bet you're all wanting to talk to me about this one, aren't you? Right, you make this salt, which has got a minus there, and potassium there, minus there, and potassium there. You're also going to make 2 H2Os. You can draw it like this. You'll do more of this at A2. But that's what happens. You make this potassium ethane dioate salt. Tough that. The point about it is you're gonna need 2 of these to make 2 of these, and you'll make 2 H2Os. You could write this, I imagine, as K2OOCCOO. Alright, I know. That could have been a sticking point for some of you. Calculate the enthalpy change per mole of water formed. So you're going to have to work out how much water is formed later on. Well, if you know how much of this is used or how much of this is used, you can work out how much water is formed. We'll come back to that later on. So imagine now that you're in this situation in an exam, you've just come across this difficult one, but you know the rules about Q equals MC delta T. You can still get marks for Q equals MC delta T. Calculate the enthalpy change per mole of water formed. So let's do our Q. Q equals MC delta T. M, 25 plus 75, that's 100. C equals 4.18. Delta T equals 3.2. Notice that it increases, so it's exothermic. Let's get these marks anyway. So you think, oh God, I'm having a nightmare in this exam. What's going on? You still get your marks, okay? There is stuff to be learned from this. I've had my bit of a shambles with the graph. You might have been having a tough time with this. Alright, so joules is 1337.6 joules. So that's 1.3376 kilojoules. You've got yourself some marks in the bank there. Alright, so now we need to work out the per moles, and specifically the per moles of water. So I've been given that this is 25 and 0.8 moles per decimeter cubed, 25 centimeters cubed and 0.8 moles per decimeter cubed, and I've been told that this is 75 of 0.6. So I'm going to have to work out the limiting moles of reactants, and therefore that will determine how much water is formed. This is as tough as it gets. I'm telling you that right now. Alright, 25 times 0.8 divided by 1,000. I've got 0.02 moles of this. You'd have loads of space to work this out in a real exam, by the way. 75 times 0.6 equals that, divided by 1,000. 0.045. Alright. If I've got, so cover one up. If I have 2 moles of this, I need 1 mole of this. So if I've got 0.05 of this, I need 0.0225 of this. I haven't got enough. This is limiting. This is excess. I'll double check it. If I've got 0.02 of this, I need 0.04 of this. I've got more than enough. This is in excess. So the limiting reactant is this, and they want it per mole of water formed. So from my equation, 1 mole of this forms 2 moles of water. So the number of moles of water formed is 0.04. 0.04. moles of H2O formed. You wouldn't have a chance, would you, if you didn't have the equation? So don't freak out about it. Alright, I wonder if there's error carried forward from the equation. I wonder that. Error carried forward on Mark 2 and Mark 4. You know what, if you wrote an equation that was wrong, but you've done the similar sort of process as this, you'll still be alright. Anyway, my final step then is to work kilojoules divided by moles. You might have to rewind that bit of the video and watch me do it again. 1.3376 divided by 0.04, 33.44. Does it give me a range? Because they say 33.6. Yeah, it does. 33.44 kilojoules. It feels like they're going to ask me for sig figs as well. No, but I'll do it for practice. 2 sig figs, 33 kilojoules per mole. Because that's 2 sig figs up there. That's 2 sig figs there. Right, in a similar experiment to that in part E, the enthalpy of neutralization for the reaction between sulfuric acid and potassium hydroxide was found to be minus 57 kilojoules per mole of water formed. Minus 57 kilojoules per mole of water formed. Suggest an explanation between this value and the answer to part E. Alright. If you were unable to obtain an answer, you would assume it was minus. So what they're saying is, when you've used sulfuric acid and potassium hydroxide, it's minus 57, and we used in the previous one ethane dioic acid. Ethane dioic acid is a weak acid. Sulfuric acid is a strong acid. I think it's just that. Sulfuric acid, strong acid compared to ethane dioic acid, which is a weak acid. They both go to completion, but you have to break these bonds in the weak acid. Right. That whole question is very year 13. It's not super duper hard. I mean, I've just done it, but it's not super duper hard. But there's plenty of barriers there for your understanding there. But look what happened in the middle of it. There was still a Q equals MC delta T, a moles, a limiting reaction question, reading the question carefully per mole of water formed, which is a weird thing to do, but we did it. So, there you go. I bet you just tune in just to watch that video, don't you? A value for the enthalpy of combustion of an alcohol can be determined using the operator shown in the diagram. Heat loss, heat loss, heat loss, heat loss. The experiment can be repeated using different volume of water that would result in a more accurate value for the enthalpy of combustion because there would be a reduction in the heat loss. State a change in the volume of water that would cause a reduction in the heat loss and explain your answer. Use a bigger volume. If you use a bigger volume of water, surely you'd get less heat loss from the top because there'd be more volume of water. There'd be less sort of surface of water compared to the volume. That would be my first suggestion. What's it say? Increase in volume. There'll be a smaller increase in the temperature above the room temperature. There'll be increased contact between calorimeter and water. It's got the thing about the surface. Okay, I've never seen that question before. But if you put... I get what they mean by it. Right. If you've got a really small amount of water, it's going to get incredibly hot in this experiment. It'll get incredibly hot. It'll start boiling almost, really quite quickly because you've only got a small amount of water. Think about like the extreme, a tiny, tiny amount of water. It'll get really, really hot really quickly. And because there'd be a huge temperature difference between the inside the beaker and the air outside, it would leak energy really, really quickly because energy moves from hot things to cold things. If you heat a large amount of water, the temperature change won't go up by as much, so there won't be such a big leaking of energy from this beaker. I hope that makes sense. Question 8. Am I nearly there? Are we nearly there yet? Student planned and carried out an experiment to determine the enthalpy of reaction when magnesium metal displaces zinc from aqueous zinc sulfate. So they haven't put the sulfates in because it's just a spectator ion. Magnesium plus zinc ions make magnesium ions plus zinc. The student used this method. A measuring cylinder was used to transfer 50 centimeters cubed of a 1 molar aqueous solution of zinc sulfate, 50 centimeters cubed of 1 molar. The thermometer was placed in the beaker. Why are they using a beaker? Bad idea. That might come up later. 2.8 grams of magnesium, 2.08 grams of magnesium, so I've got a moles I can get there. Powder without added to the beaker. The mixture was stirred and the maximum temperature recorded. Firstly, let me just say, they're using a pretty sloppy method. They should be using this method. 1, 2, 3, miss a go, boom, 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 boom. Alright, I wonder if that comes up later. This is a sloppy method, using a glass beaker, and they're not doing it like this. They're just chucking it in, stirring it, and hoping for the best. The mixture was stirred at the maximum temperature. The student recorded starting temperature. There's my delta T. 61.2 minus 23.9. Might as well get that now. Show by calculation which reactant was in excess. Alright, well, I'll work out moles of this and moles of this and work out which was in excess. So it's 50 times 1 divided by 1,000. This is my moles of zinc 2 plus. 0.05 of zinc 2 plus, and my other is 2.08 grams. 2.08 grams divided by the MR of zinc, 65.4. 2.08 divided by 65.4, 0.0318. They react in a 1-to-1 ratio, so zinc is in excess, which means this is limiting, so that's the one I'm interested in for later on. That's the answer to the question. Zinc 2 plus, reactants in excess. You can write zinc 2 plus or zinc sulfate, I imagine. Magnesium. What have I done? Ah, what a fool. Stupid mistake number 2. Breathe. Carry on. Right, 2.08. I divided by the MR of zinc because I'm tired. Divide by the MR. That's 2 mistakes on 1 bit. Oh, it's bad, this. It's not my finest hour. Hopefully this is, some of you have seen a bit like what it happens with you lot. That's in excess. Magnesium's in excess. Dope. Part of me thinks, part of me's like, should I just do it all again and video it again? And then the main part of me is like, no. I'm alright with it. I'm alright with making mistakes. Enthalpy of reaction. Right, so, other way around, that's my excess. Magnesium is my excess. That's the number I'm going to need later on because that's my limiting. Sorry about the mistakes, but maybe I had some of you shouting at your screens, telling me I'm a fool. Right then, what do I need to do now? Enthalpy of reaction. So there's my moles, 0.05. So I just need to do my Q equals MC delta T bit. Let's see if I can get through this bit without mucking it up. M, 50, C, 4.18, delta T. Where did I write that? 37.3. I can do this. I can do this. Come on. 50 times 4.18 equals times 37.3 equals that. Press the button. 7795.7. 7795.7. The crowd go wild. He's nearly there. 7.7957 kilojoules. Now, because all I've got to do is divide by the moles. The end is in sight. Divide by 0.05. 155. Nah? No, come on. I kept it in kilojoules, didn't I? Dope. 7.7957 divided by 0.05. 155. I knew it just didn't look right. So that's not a mistake. That's just I knew I'd kept it in joules. That doesn't count as a mistake, alright. Right, and then you do 155.914, and then I've got to decide on the sign. Surprised I remembered that. Minus. Not my finest hour, but we're there. Units, not units, sig figs, 155914. 3 sig figs, 1, 5, 6. Now I'm there. Slight recovery there at the end. Another student used the same method and obtained a value for the enthalpy reaction of this, minus 142. So theirs didn't give out as much heat. Didn't exotherm as much. A data book value is this, so we're both miles off, us and them. Suggest the most likely reason for a large difference between the student's experimental value and data book value. The most likely reason is heat loss. Alright, heat loss from the equipment. Suggest how the student's method and the analysis of the results. Method and analysis of the results. Clue. Could be improved. You're not allowed to talk about use a better thermometer. You're not allowed to do it, and not even in that voice. Alright, this is about describing. The student should get a beaker, stick solution number 1 in it, stick a thermometer in it. You can talk about insulation, alright, that's fine. But you should then go, they should take temperature readings for the first 1, 2, 3, 4 minutes maybe. On the 4th minute or the 5th minute, they should add the zinc powder and stir. On the 6th minute, they should record the temperature. On the 7th minute, the temperature. The 8th minute, the temperature. The 9th minute, the temperature, and so on. Then, extrapolate both lines to the 4th minute and read the temperature change. That is the analysis of the results. This gives you a more accurate delta T, which you would then put into the Q equals MC delta T to give you a more accurate value. Alright. Justify your suggestion. So justify your insulation to minimize heat loss, and then justify this because it gives you a maximum temperature that would have been reached if there was not heat loss. Let's see if that's enough. Justification. Insulate. Record for suitable time before and record after, and extrapolate. The only other justification I forgot to mention was this one. Why record at the start so it can reach room temperature? Why record after so you can get the natural cooling curve of the equipment? So this question, this is the required practical. You can't just keep going on about insulation. You'd only get 1 mark. Insulation to reduce heat loss would not get you any more than 1 mark, maybe 2, if you explain it really well. Alright, that's me done. That's your lesson. See you later. Have a nice weekend, everybody.